Hello all. So today in this session I would like to cover one of the most important topics in the context of machine learning and deep learning, which is called as introduction to gradient descent. Okay, so gradient descent is basically an optimization algorithm which is widely used in both machine learning and deep learning, and the reason why we use gradient descent is to minimize the cost function. When I talk about cost function or loss function, it's nothing but the difference between the actual value and predicted value, right? So when you want to have more good accuracy, okay, so we have to reduce the cost function. Cost function is nothing but the error. Okay, so when you reduce the error, the accuracy will obviously be increased. Okay, so the difference between the actual value and the predicted value has to be gradually reduced, that is by reducing cost function. And how do we do that? By applying some optimization algorithms, and one such optimization algorithm we apply to reduce the cost function is gradient descent. Okay, so how do we do that? We reduce the cost function by iteratively moving in a direction of the steepest descent as defined by the negative of the gradient. Okay, so I'll explain you what is all this in detail in the coming slide. So it is actually a more important concept for you to understand when you are training your machine learning models, particularly the supervised machine learning task which we have started working on, that is regression and classification. Okay, so I have already told you, like in the first units we were discussing about a lot of statistics, because machine learning, all the machine learning algorithms works on statistics, that is mathematics, when you talk about linear regression or logistic regression, right? So in statistics, the machine learning or data science or in any other field, we optimize a lot of stuff. Okay, so for example, when we talk about linear regression, we optimize intercept and slope, right? Because of the changes in intercept and slope only, we have different variations in the predictions, right? So we do that. When we talk about logistic regression, we optimize the squiggle, right? So a good example is the sum of squared residuals in regression. When we talk about machine learning, okay, so sum of RSC is nothing but one type of loss function, and the residual is the difference between, residual is nothing but the cost function, which is actually the difference between the observed value and the predicted value. Okay, now as you can see here in the figure, I have height and weight. I want to predict the person's height with respect to the weight. Okay, now the straight line is nothing but the actual value, straight line is nothing but the predicted value, the dots are nothing but the actual value, and the difference, the red color dotted line that you see, the gap between the straight line and dot is called as the error. The red one is nothing but the error. Okay, now I want to reduce that particular error. Okay, so as you can see, the above figure shows on the y-axis the sum of squared residuals. Okay, and on the x-axis we have different values for the intercept. Okay, so we first start with the point on the y-axis, which actually represents the sum of squared residuals when the intercept is actually equal to 0. Now what do? We continue to plot the points. Okay, we continue to plot the points in the graph based on different values of the intercept. Okay, so the lowest point in the graph, okay, so here the lowest point in the graph has actually the lowest sum of squared residuals. Okay, now this gradient descent algorithm will actually identify the optimal value, not the highest value or not the lowest value. It actually identifies the optimal value by taking big steps when we are far away from the optimal sum of square residual, and will start making steeping the solution or steeping the steps to get the best solution. Okay, for getting this, we actually calculate the derivative of each point of the function created by the points. Okay, in other points, we are simply trying to calculate the derivative of the loss function. So I'll take this step. Okay, so when you see intercept and sum of squared points, what we are trying to do is we take baby steps when it is close. Okay, so when you see that the optimal point is near to the existing data points, we take very small steps to reduce the loss function. How do we do that? By taking the derivatives of the loss function. Okay, now why is this gradient descent actually required, and how does this gradient descent works? Okay, so when you're training your machine learning models, our main goal is to minimize the loss function, because when you minimize the loss function only, you can improve the accuracy of the model. Okay, so for regression we have seen MSE and MAE. For classification we have seen cross entropy loss. We have binary cross entropy for loss for binary classification. We have categorical cross entropy for multi-class classification, right? So when you look into this particular figure here, the gradient descent uses the derivative, okay, derivative of the loss function to find where the sum of residuals is actually lowered, though this is the minimum point, which is the average point which I can lower. Okay, the closer we get to the optimal value for the intercept, the closer the slope of the curve gets to 0. Okay, so basically understand that this particular gradient descent uses the derivative in order to find the sum of the squared residuals, which is the lowest. Okay, so what happens if we do that? The closer we get to the optimal value for the intercept, the closer the slope of the curve gets to 0. Okay, now how does this gradient descent know to stop taking steps? Okay, once I found out one, how does it know that we have to stop the steps? Okay, so basically there is one hyperparameter called as learning rate. What is that hyperparameter? Learning rate. It is a very small value which we will actually multiply with the slope. Okay, so we define the step size with respect to slope and this hyperparameter which is called as step size. Okay, so the step size will be very close to 0 when the slope is very close to 0. This is how we identify. So the gradient descent actually stops when the step size becomes close to 0. And how do we know that? Because we multiply the step size with the learning rate, which is the smallest hyperparameter. Okay, so the minimum step size that we take is 0.001 or even smaller. Okay, so this will not affect on the performance of the model. So gradient descent actually includes a limit of number of steps it will take before giving up. Okay, so in practice the maximum number of steps that you can take is equal to 1000 or greater, and the step size value is very small, which is 0.001 or smaller than that. Okay, so we can also estimate the intercept and the slope simultaneously. We can use different types of graphs, and we can also plot different values for intercept and slope. Okay, now how does this gradient descent work? As I told you, the gradient descent works by taking the derivative of the loss function. Okay, so the process of gradient descent involves by calculating the partial derivative of the loss function with respect to the model's parameters. Okay, so here I give it as theta. Okay, the parameter rule is theta. Theta minus alpha into dou j of theta by dou theta, where alpha is nothing but the learning rate, which I told you, the step size for the updates, and j of theta is nothing but the loss function, and this is nothing but the derivative gradient of the loss function with respect to theta. Okay, so just understand that calculating the derivative of the loss function is nothing but gradient descent. Okay, so when we talk about steps in gradient descent, first is take the derivative of the loss function. Next, pick some random values for the parameters, plug those parameter values into the derivatives again, calculate the step size, calculate these new parameters with respect to change step size, and go back to step 3 and repeat the process until and unless you get the minimum loss function or the optimal solution. As I told you, learning rate is used in the calculation of the step size, which is actually a hyperparameter which will actually control how much are we adjusting the weights with respect to loss function, because the weights cannot be adjusted too drastically. Step by step, slowly we have to change the weights, and that is done with respect to your learning rate. Okay, so what will happen? This will make sure that we do not miss on any local minima. Okay. Now, when I talked about gradient descent types, we have three important types of gradient descents. One is called as batch gradient descent, second one is called as stochastic gradient descent, and third one is called as mini batch gradient descent. Let's look into each one of them. When I talk about batch gradient descent, it uses the entire data set to compute the gradients. That is, whole data set is considered at a time, okay, as a batch. Okay, so we use this when you want to converge all the data points steadily, and then the drawback of this is computationally expensive, because when you have large data set, processing such huge data set once would be complicated. Okay, second is stochastic gradient descent. This is nothing but using a single data point to compute the gradients. Suppose you have 100 values in the data set, for every 100 values you calculate different gradients. Okay, pros, faster updates because we are processing only one data point. Cons is noisy update, which can lead to fluctuation, because every point change has to be processed, hence we may get noisy updates. And the last one is mini batch gradient descent, which is nothing but small batches of data. The entire data is divided into some subset of small batches. First one is entire data, second one is single point data processing, here batch of data. Okay, so to overcome the trade-off between stochastic and batch gradients, we go for mini batch gradients. Okay, so this balances the difference between batch and stochastic, which is commonly used in practice. Still computationally demanding, but this is the most efficient one when you compare all the other parameters. Okay, so this is all about how do you get that steep size. Okay, so batch gradient, all are processed at once, there is no change that you can see. Stochastic, you can see so much of noise being introduced in the cycle. And mini batch, not too plain, not too curvy, but you get the optimal result, with which we go for mini batch gradient descent. Just understand that gradient descent is optimization algorithm which is used for reducing the loss function. Okay, so how do we do that? By calculating the derivative of the loss function. Okay, thank you so much.